This presentation describes the sender's remote OpenGL command stream system. This system uses the standard OpenGL ES, and that is used to generate graphics that is remote. Normally this system deals with local graphics. A sender has a revolutionary process which allows to use this OpenGL format as a remote graphic system. The advantage here is that the application, the graphical application, which might be a game or a business system, does not have to be recompiled. We use systems as they are, and we envelop it in a system which extracts the OpenGL commands. First, we'll look at the diagram of a local application, standard Unix, let's say, or it could be Apple, it could be other operating systems, Windows. A local app that does graphics, first of all, has a CPU, which can do computation. It has software which implement the API of OpenGL ES, which consists of hundreds of, if not thousands of APIs. It has an application which is written by not the end user, but the program provider or the application provider. It consists of the logic of the program, if it's a game or possibly business logic, and it has a way of doing graphics. It uses the OpenGL ES library that comes standard on systems, and in combination with a device-specific GPU, which allows it to render millions of pixels per second. It also was connected to the input devices, a keyboard, a mouse, or a game console. And that is the standard way of running games, and it could be a mobile system, it could be a desktop system. It still is the same basic principles. For an example, Android uses OpenGL ES as its graphic system. So to put anything on the screen, you have to use the OpenGL ES system. There is other standard which is called OpenGL, and it's a little bit larger standard. It's very similar, but it's quite larger than OpenGL ES. OpenGL ES was originally meant for mobile systems. The previous system dealt with a single computer which ran the application and the graphics. Now we're going to try to make a system where the graphics are done on a client computer and the actual gameplay, the logic of the game, the application or business application, is done on a remote server. And we won't be discussing why this is an economical way and a very frugal way of doing remote games. Okay, so what we see here is we have two computers. We have two CPUs, and in this case here we have two OpenGL ES stacks, and we have an application which is on the server alone. So the application, which might be a game which does intensive graphics, would normally be done on a CPU. Instead, we take a representation of the graphics of OpenGL ES and send it on a server. The client send it from the server to the client. The client gets this stream and takes the generated OpenGL and sends it to the OpenGL library, and that goes into the CPU, which gives the commands for the GPU and does both the display is done on the local client and the input devices are on the local client. The remote server deals only with running the game and it does not do any rendering. In this demo, we will demonstrate two large OpenGL ES applications. One is the standard benchmark for OpenGL ES, and it covers a lot of the graphics that can be done. And the second one is a much larger application, which is the MAME system renderer or game renderer mostly. And it consists of thousands of individual games with different architectures. Both of these programs can generate OpenGL ES code. So basically, once we have a server client running properly, we can take the MAME large application and run all the clients, and all the games that are emulated should run properly. Okay, we'll start out with the benchmark of OpenGL ES. Okay, this is the benchmark, and it's as you see, a three-dimensional benchmark which has fairly nice and smooth graphics. It runs in about 10 seconds. And the next thing we'll do is run it at 15 frames per second, because we see this is a benchmark for OpenGL. It runs 1783 times a second instead of 60, which we want to go. So the next thing we'll do is using the make program, we'll send out a same exact program. You can't tell a difference, but it works at 60 frames a second, which is the display rate, so you don't really gain too much in going faster on this display. Okay, so now we want to run a unconstrained frames per second and generate a command stream. So it's make 3. What we do here is we run it, and it'll run it with many frames per second, over 1,000, close to 2,000 frames per second. If we just run it, if we just read that file that was generated, right, we generated a file with a unconstrained number of at 60 a second, and now we're running it at 1700 per second, and we see that it runs the program extremely fast. What was 10 seconds is now 1/3 of a second. So in this demo, we will now go to everything running at 60 a second, and everything should run at the proper speed. Now we can, this is the 60 second. It's now reading the same file as previously, but displaying it at a maximum of 60 frames per second. Okay, the next demo is a simultaneous server and client. So let's start it up. We simultaneously run the server and the client, and they're connected over a command stream channel. So here what we see is we have, on the right side we have the server, on the left side we have the client. You see how well synchronized they are. Let's run it one more time. What we do is have it's all running, of course, on one machine, different processes. The right-hand process is running the actual application, and it's also displaying in this case. Normally, for many applications, the display on the server is not really needed, and we see that the client is perfectly synchronized with it, and both in time and in the graphic quality is exactly equal, because we're both getting the same command stream, OpenGL command stream. Okay, now we will continue and we will consider a program which is, or a series of opus of hundreds of programs on mostly legacy programs, and there's a public domain free software that will allow you to run all these games, and the server of this, the program name MAME, will generate OpenGL ES. So if we now run the next version of our program, it's called Make 7, it runs the MAME program. So here we see the MAME program and we see the console. I could take the mouse and move it around. Let's go unfiltered, and we get an idea of how many things, how many programs. Right, it goes on for another 5 minutes. Let's look at the available programs. We'll look at 2 programs of interest, which is a poker program and a super tank program. Okay, so let's stop this. This has been recording at a few thousand frames per second. Now let's run it with writing a command stream in parallel and at 60 frames a second. So it uses only a small fraction of the speed that it can do, the rendering speed that it could do. Okay, so we're running the program now. It's at 60 frames per second, and it's writing a command stream in parallel. Okay, so I can go up and I can go down. I can go down and I can go up. Let's go to unfiltered. I can move the mouse around, use the mouse. I could use the keys, page up, page down. I could use the incremental key, and I can move the mouse around, and it also will be reflected in the output of the OpenGL. Right, so I've created now an OpenGL, and I can play it. The next thing to do will be to play it. Okay, I'm now gonna play back the file, that the OpenGL file, which was command stream file, which was previously written. Okay, I'm not touching anything now, and you'll see that the mouse moves and the cursors move. Everything really moves, and it moves quite smoothly and quite fast. There we go. It's a swipe using the scroll bar key. The next thing we want to do is try to see if we can run the same program simultaneously, write a command line stream. Let's see what we have here. Okay, let's wait a second. The next program is 10. Run it at 60 frames a second. Now we're going into Super Tank. I can press on 5, it'll go into a coin mode. I'm getting credits, and then I can press 1. We'll now start off the game. I'm using the mouse now to play. The next thing I want to do is to read the previously written command file, command stream, and see that we can see exactly what was done previously. I'm now going to press the 5 button. I'm putting in credits, and I'll press the 1 button because I want to play single user. And should be able to hear the, you don't hear it because it's actually not, the audio has not been recorded. That's something that should be done. Okay, the next thing we want to do is to see if we can have a server client and run them both simultaneously. So what is done on, in this case, the keyboard is on the server and the audio is on the server. In probably normal cases, the keyboard and the audio would be on the client. So let's run it now. Okay, so what we have here is we have 2 windows. I'll separate them. Let's do it like that. And the server is on the right hand side and the client is on the left hand side. So I press a key to continue. Okay, I can press the 5 button, puts credits in, and we notice they're exactly the same. What happens when it's, you can't tell which one is before the other one. They're really quite well synchronized. I'll push 1. I'm playing the game now, not that well. I'm not recording now, it's going out dynamically. Okay, so we see how we can play a game. What normally would happen is the server would be without a display and without a keyboard and without a GPU, in fact, and it would run very interactively and very good response. Okay, we'll try one more game. Let's run make 13. It's a poker game, so it just shows you can play the standard types of games. Let me put money into this, getting credits, and I'm not sure exactly how to deal. I guess I'll hit 1. Insert good luck. Push hold. Oh, I want to do hold. How do I hold? H for hold. Don't know. What I can do is to, since I just recorded it, we can play it back and we'll see. It should be, we should be able to get the same thing we saw previously. So make 14. Okay, I'm inserting the coin now, pressing 5 for inserting coin, M for dealing, hold is R or something like that. Okay, this is just